Hello everyone, this is Harrison. Today I'm going to show you how to solve problem 23.49 of Mastering Physics. Okay, let's begin. So the problem is shown from above in the figure is one corner of a rectangular box filled with water. A laser beam starts 10 centimeters from side A of the container and enters the water at position X. You can ignore the thin walls of the container. Okay, so this is the image. And the first question is, if X is 15 centimeters, does the laser beam refract back into the air through side B or reflect from side B back into the water? Okay, so in order to answer that question, we need to draw this image into a diagram. Okay, let's begin. So first of all, we have side A. Okay, I will draw here side A and then side B. They are perpendicular, of course, and we have a light beam goes like this. It enters side A of the container. This side is 10 centimeters. I will call this side is A, which is 10 centimeters, and this side is X, which is 15 centimeters. And the index of refraction of the air is N1 is equal 1, while the index of refraction of the water is N2, which is 1.33. And when the light enter the container, because the water has higher index of refraction, the light will be bended toward the normal. This is the normal, and it will be bended toward the normal. So it will go like this, and then hit the side B of the container. And in order to know this light is refract out to the air or reflected back to the water, we need to compare this angle with the critical angle. I will call this angle is theta 3. This angle right here is theta 2, and the first incidence angle, or the angle of incidence, is theta 1. Okay, so let's begin. First of all, we can find the critical angle, and the critical angle in this case is this the formula. Sine of critical angle is N1 over N2. N1 is 1 and N2 is 1.33, and it is, let's calculate, 1 divided by 1.33 is 0.752. Okay, so 0.752. That means theta C will be equal inverse sine of 0.752. Okay, so now inverse sine of 0.752 is 48.8 degrees. 48.8. So in order to find out whether or not the light is refracted, we will need to compare theta 3 with this critical angle, and this is how to find theta 3. First of all, we need to find theta 1, and by using trigonometry, you can see that tangent of theta 1 is equal to opposite side, which is X, over adjacent side, this side, which is A, X over A, and X is 15 centimeters, while A is 10 centimeters. 15 over 10 is 1.5. Therefore, theta 1 is the inverse tangent of 1.5, and that is 56.3 degrees. Okay, now 56.3 degrees. Next, we need to find theta 2, and in order to do so, we will apply the Snell's law, and that law is n1 sine theta 1 is equal to n2 sine theta 2. That means sine of theta 2 will equal n1 over n2 times sine theta 1. n1 is 1, n2 is 1.33, and sine of theta 1 is sine of 56.3 degree, and that is equal to 1 divided by 1.33 times sine of 56.3 degrees is 0.626. Okay, 0.626. That means theta 2 will equal to the inverse sine of 0.626, and that is 38.8 degrees. 38.8 degrees. And right now, let's look at the diagram for a moment. You can see that theta 2 and theta 3 are complementary angles. In other words, theta 3 will be equal to 90 degree minus theta 2 and 90, and then we will substitute theta 2 by this value, 38.8 degree, and that is, let me see, we can use the calculator to make sure. 90 minus 38.8 is 51.2 degrees. Okay, so here 51.2 degrees, and you can see that in this case theta 3 is 51.2 degrees, while the critical angle is only 48.8 degrees. Theta 3 is larger than the critical angle, therefore the light will be reflected back into the water instead of reflected out to the air, and that is the correct answer of this question. Yeah, the light is reflect from side B back into the water. And also for part B, determine the angle of refraction or reflection. Yeah, we just figure out it is 51.2 degrees, and that is almost equal to the answer of mastering physics. The problem is they round the number different than I did. Yeah, so okay, now let's move to the next part C. What is the angle of refraction or reflection at side B if x is equal to 25 centimeters? Okay, now we have a second value for x. However, we still use the same formula. We only need to change the value. We only need to substitute x for 25 centimeters instead of 15 centimeters. Okay, so now this time x is 25 centimeters. And like before, we will find theta 1 first. But this time, tangent of theta 1 is x over a, but this time is 25 centimeters over 10 centimeters, which is 2.5. So theta 1 will equal to inverse tangent of 2.5, and that is inverse tangent of 2.5 is 68.2 degrees. see 68.2 degrees. And then Snell's law, I will skip to this step. So sine of theta 2 will equal to n1 over n2 times sine theta 1, and n1 is still 1 and n2 is 1.33. Sine of theta 1, this time theta 1 is 68.2 degrees, and that is 1 divided by 1.33 times sine of, let me see, 68.2 degrees, and that is 0.698. Okay, here 0.698. Therefore theta 2 will be equal to inverse sine of 0.698, and that is, let me see, inverse sine of 0.698 is 44.3 degrees. 44.3 degrees. And like the previous explanation, theta 3 will equal to 90 degree minus theta 2, 90 minus 44.3, and that is about 45, I guess. Let's check for sure. Yes, 45.7 equal to 45.7 degrees. And this time theta 3 is smaller than the critical angle, 48.8 degrees. So instead of reflected back into the water, it will be refracted out to the air. And because the water has higher index of refraction, so the light will be bended away from the normal. So instead of going this way, it will go in like a little bit this way. So it's like this. And we will have a fourth angle. I will call that one is theta 4. This is the angle of refraction. And in order to find theta 4, we will use Snell's law again. But this time, we will have another equation. And that one is n2 sine theta 3 is equal to n1 times sine theta 4. That means sine of theta 4 is equal to n2 over n1 times sine theta 3. n2 is 1.33, while n1 is 1. And sine of theta 3 is 45.7 degrees, and that is 1.33. Divide by 1 is just keep the same, so I will skip that one. Times sine 45.7 is 0.952. Okay, so 0.952. In other words, theta 4 is inverse sine of 0.952, which is 0.952, and that is 72.2 degrees. Okay, so 72.2 degrees, and that is the exact answer of mastering physics. Let me show you. See, theta 72.2 degrees. Okay, now then we will move to the final part, part D. Find the minimum value of x for which the laser beam passes through side B and emerges into the air. So we know that so if the light want to refract it out to the air, the angle theta 3 must be smaller or equal to the critical angle, this angle. So in order to know what is the minimum value of x, we will find that from theta 3. So we will use exactly the same formula but in the opposite direction. So now we have theta 3 and then we find x. Okay, let's begin. So this time theta 3 is 48.8 degree, which is the critical angle. And we know that theta 3 and theta 2 is complementary. I said that earlier. So this time theta 2 is 90 degree minus theta 3, which is 90 degrees minus 48.8 degrees equal to about 40 maybe. 90 minus 48.8 is 41.2. Okay, 41.2 degrees. And now we use the Snell's law, but instead of finding theta 2, we find theta 1. Yeah, so we use this formula. And this time we know that sine of theta 1 is equal to n2 over n1 times sine of theta 2. n2 is 1.33, n1 is 1, and theta 2 is 41.2 degrees. Okay, let's calculate that. 1.33 divided by 1, which stay the same, times sine 41.2 is 0.876. Okay, where is it? Okay, 0.876. That means theta 1 is the inverse side of 0.876, and that is 61.2 degrees. 61.2 degrees. And we know that tangent of theta 1 is x over a. Yeah, tangent of theta 1 is x over a. Therefore, x will equal to a times tangent theta 1. A is 10 centimeters. That is the constant. Yeah, the accurate value. And tangent of theta 1 is tangent of 61.2 degrees. Okay, so this one, 10 times tangent of 61.2 degree is 18.2 centimeters. Okay, 18.2 centimeters. And that is the answer that Mastering Physics is looking for. And that actually makes sense because 18.2 is larger than 15. Where is it? Yeah, so it is larger than 15, but when it is actually it is like smaller than 25 centimeters. So because 25 centimeter is like from the first part, the part A. So in part A, we know that when x is 15 centimeters, the light is reflected back into the water. So in order for the light to refract it out to the air, x must be larger than 15 centimeters. And in this case, it makes sense. Okay, thank you for watching. I hope this helps you solve the problem 23.49 of Mastering Physics. Hope you can solve the rest of the homework. Okay, thank you. Goodbye.